Welcome back to our course on memory device technology for AI/ML computing. I'm your instructor, Dr. Shubhadeep from IIT Hyderabad. So, in the previous lecture, we started discussing about the DRAM cell and the DRAM memory subsystem on a whole. We saw a very brief introduction and a historical overview of the DRAM memory architecture. And we saw that the main bottleneck when it comes to modern day computing system is the fact that there is a big gap in the throughput and performance of processors and the main memory. This is because while transistor scaling and multi-core operation has made the throughput of processors very, very fast, DRAM scaling and speed improvements in the main memory have been much slower. As a result, there is a big divide or big gap which keeps growing year on year. And this difference in throughput is why we are having a big bottleneck at the CPU and main memory interface, right? And we also saw that the problem becomes much worse when you have data intensive AI/ML based computations. Looking at the solutions, we discussed that there is a traditional approach of trying to do very smart DRAM subsystem, which includes parallelism in the access of data from the CPU to the DRAM subsystem or the main memory subsystem. And there is also another approach which involves having embedded DRAM, improvements in packaging technology to reduce the interconnect delay. So in today's class, we will begin with understanding the DRAM subsystem architecture. Now, the DRAM subsystem architecture is really, really interesting and fascinating, and that is what we will deep dive into today. Okay, so just to remind you, as we have discussed in the previous slide, that both advances in DRAM cell scaling, that is reducing the capacitor size and making the interconnects faster, plus what we are going to discuss today, improvements or innovations in the memory subsystem architecture, both coupled together has enabled the main memory of computing systems to be very dense and very fast. Okay, and all of this has happened at a relatively cheaper rate. Cheaper compared to, of course, the very expensive cache memory. Now, how is the DRAM subsystem look like? Now, the DRAM subsystem, because of its complexity, is again organized in an hierarchical fashion. What is the reason for having the hierarchical fashion? It is the same why the entire memory subsystem also was organized in a hierarchical fashion. It is to try to optimize between capacity and latency. Now, this is looking more like the movie Inception, where there was a memory hierarchy, and within that small slice of memory hierarchy was your main memory, consisting of your DRAM subsystem, and within that and now we are seeing that DRAM subsystem also consists of a memory hierarchy or a subsystem hierarchy. However, in this case, the pyramidal structure is inverted, as you can see in the image that I have shown on the left hand side of the slide. Why is the pyramidal structure inverted? This is because on the top of the pyramid always consists the processor subsystem, right? And at the bottom is your 1T, 1C DRAM cell. Okay. So at the top, you have the interface which gives you 64 bits or whatever the word length of the processor is to the processor at the top of the hierarchy. And this is facilitated by this concept of channels. Channels are basically the slots that you see on the motherboard of your computer, in which you insert the main memory or the DRAM chips. I will show you that in future slides. And at the bottom of the hierarchy is just one cell of one transistor and one capacitor, through which you get 1 bit of data. Okay. Now, as we have discussed that the 1T 1C memory array itself is, or the 1T 1C memory cell itself has a lot of nuances and intricacies, and we will discuss that in detail in the coming lectures. Next 2 lectures will be dedicated only in understanding the 1T 1C cell, its architecture and also its operation, the read, write, hold and refresh operations. But in this class, we will start from one hierarchy above, and that hierarchy is something that we are already familiar with. This is the second part of the bottom of the pyramid. So we are starting our discussion building top down from 1T 1C, which we will discuss later. Next, let's start from the bottom of the pyramid, which is the memory array. So the bottom of the pyramid is the memory array consisting of row and columns. Okay. As we have discussed in detail in our earlier sections where we were talking about a generic memory array, in the generic memory array, we saw that you give an address to the memory array, and the row, one part of the address goes to your row decoders, and that selects one particular row. In this case, as you can see, this particular row has been selected, the one that I have marked out, and all the corresponding columns of that row are read out, and from the column marks, you get an n bit of data. This is the generic architecture that we had studied in our second week. However, in the DRAM, the operation is slightly different. In the DRAM, the output of one array is just single 1 bit, not multiple bits, but just single 1 bit. Okay. How is this facilitated? This is possible because the address, a part of the address goes to your row address or the row decoder, which selects one of these rows, and out of all the different columns in that corresponding row, only one is selected. In this case, you see that in this case, you can see that the one which is marked red is actually selected. Only the one intersection of row and column, which is 1 bit consisting of one DRAM cell, is selected. Just important to note that each of these small cells consist of this 1T 1C element. Okay. So as we have just discussed, the bottom of the hierarchy is your one memory array through which only a single bit is selected. How is it selected? Through the row decoder and the column marks. Okay. Next, we come to a very important concept. So from row column array, we are moving on to the next element in the hierarchy, which is called the bank. Now, the bank is a very, very important functional element in DRAM, and we will discuss why that is the case. But for the time being, let us understand what is the constitution of a bank. So a bank consists of 8 such arrays or pages. See, I have shown you one memory array over here and 8 such arrays. 1, 2, 3, 4, 5, 6, 7, 8. 8 such arrays, or sometimes even called pages, constitute of one single bank. Okay. So 8 arrays constitute of one bank. The very interesting thing to note, which might be a little counterintuitive, is that the same column and row address is given to each of the pages or each of the arrays in the same bank. And as a result, as you can see in this diagram, if I zoom in, since each of these arrays are receiving the same row and column address, the same corresponding element which I have marked out in red and in blue. In red and blue, the same particular element in each of the arrays is selected in one single bank. I hope that makes sense. can be a little new, so let me just repeat. One bank, which is the next element of your DRAM subsystem hierarchy, consists of 8 pages or arrays. Since the same address and row is sent to each of these pages, the same memory element is read out, or the same location in row and address is read out from each of these pages. And since one output is for one of the pages, all of them are collated. See, all of the addresses are getting collated, or all the data is getting collated. One output from each bank is getting collated, and therefore the output of one bank is 8 bits or 1 byte. Okay. Why is this concept very important of banks? Because of a very interesting concept that we will introduce in the next slide, that of interleaving. Okay. So as we have just spoken, the first two elements are the memory array. From each memory array, only one bit is selected. 8 such memory arrays or pages constitute of one bank. Therefore, the collection of 8 bits from each of the banks from the same memory location in each of the arrays constitute of the output of a bank. So the output of one bank is 8 bits or 1 byte. Next, we will go ahead and discuss the very important concept of interleaving, which makes DRAM subsystem very interesting. So let us understand the concept of interleaving with a very intuitive example. Suppose I want to store the following string into my memory location, and the strong string, it can be any string. I am just, for the sake of example, taking the name of our course, Memory, Devices and Technology. This is just an example. Memory, Devices and Technology, if I want to store in memory in a DRAM array, what would be the way to do it? And a common sense approach would be, you take just one of these memory arrays, which we have shown in the previous cell or previous slide, and you store them one by one. Right? So in one array, because this is contiguous data, memory, devices and technology, they appear together, you have them stored at different memory locations in the same array as memory, devices and technology. Right? This is what common sense would suggest. However, that is not what is happening in case of a DRAM subsystem. And this is where the concept of bank becomes very important. How actually data gets stored in the DRAM subsystem is in different banks. Okay, and this is the very interesting concept of interleaving. So as you can see, the same data in DRAM subsystem is stored in different banks. So memory gets stored in the bank 0, devices get stored in bank 1, and gets stored in bank 2, and technology gets stored in bank 3. Just remember, these are just examples. So memory, devices and technology not just get stored in the same array. It does not even get stored in the same bank. It gets stored in different banks. And this is the very interesting concept of interleaving. So a natural question would be, why are you making life so complicated and difficult? Definitely it has a very important advantage. So this is the question we will try to ask and answer in the next slide. Why are you storing data across different banks? Why are you implementing this concept of interleaving? And to understand this, let us see this following GIF, which I have picked up from the Wikimedia website. This explains the concept of interleaving very beautifully. So let it reset. For example, I want to store number 0, 1, 2, 3, 4, 5, 6 and 7. As you can see, you are not storing the value 0, 1, 2, 3, 4, 5, 6 and 7 sequentially in the same bank. However, you are dividing them up into different banks. One, you're 0, 0, you're storing in the bank 0. Then in bank 1, you're storing 0, 1. Then bank 2, 0, 2, so on and so forth. The question is, why are we doing that? You are doing this because, as you can see in the animation, the red, whenever a bank is red, it means that it is not operational, not functional, not available for reads and writes. Why is this the case? Because remember, DRAM consists of this 1T 1C cell. This 1T 1C cell has to be dynamically refreshed again and again to make it remind what was the data that was stored in the storage node. This is because of the leakage through the capacitor, and we will study that in detail, but I have already described what is the meaning of dynamic in DRAM. The meaning of dynamic is that the data has to be continuously refreshed, and because you are refreshing the data continuously, there are certain periods of time in a certain in the memory array, more specifically in individual banks. So every bank is being refreshed one after the other. So first you see bank 0 was at this instant of time. If I just pause this, if I take a snapshot in time, we will see that at one point of time, only the bank which is white in color is available for read and write accesses. Rest of the time, the refresh operation is going on. And this is why you implement the concept of interleaving. So interleaving compensates for the slow DRAM refresh by spreading data evenly through the banks. Just imagine if you had stored data sequentially, the amount of time that it would have taken for you to recover the data would be much larger. This is because after each read and write, or maybe a bunch of reads and writes, you would have to wait for the bank values to get refreshed. Okay, this is the key concept of interleaving. More importantly, by spreading out the contiguous memory accesses, both in read and write, your throughput of your memory becomes larger because your wait times are significantly reduced. So using this concept of interleaving, we are able to improve the throughput at the bank level. So I hope you have understood this very interesting concept of interleaving and why banks are very important. Next, we move on to another part, or the next element in the memory hierarchy, and which is your chip. So remember, the bottom of the memory hierarchy consists of your 1T 1C memory cell. A bunch of 1T 1C memory cells constitute of an array. 8 such arrays constitute of a bank. Now let's see what is a chip. Very interestingly, 8 banks, when they are put together, they constitute of a package chip. So these are 8 such banks: bank 0, bank 1, bank 2, bank 3, bank 4, bank 5 and till bank 7. So 8 such banks, when they are put together, they consist of a package chip, and we will soon see the image of the package chip. Before that, let us understand what is the function of a package chip by asking the questions. We know that each of the bank gives you 1 byte or 8 bits of data. With this in mind, can you answer the question, during one operation cycle, can you tell me how many bits are part of the output of a single chip? So a natural answer would be that since one bank is giving you 8 bits of data and there are 8 banks inside the chip, natural tendency to answer would be that 8 into 8, 64 bits will be the output of one chip. But that is completely not correct. Why is that not correct? Because remember, during one operation cycle, only one bank is selected. Why? Because rest of the banks are going through the refresh, right? So the correct answer is that during one read-write access, the number of bits coming out from one chip is also only 8 bits. Only 8 bits of data is coming out of a single chip. Therefore, at one operation cycle, data is coming out only out of one of the banks. So out of the 8 banks, only one of the banks is actually operational. How do you decide which bank is operational? Again, it is the same concept. The address which goes into the memory subsystem or the DRAM or the main memory subsystem from the CPU tells which bank is to be accessed during one operation cycle. So the address now has to contain data corresponding to row, column and 3 bits of bank. Why is it 3 bits? Because 2 to the power of 3 is 8 and there are 8 banks. So this bank component in the address tells which bank has to be accessed, right? So I hope you understand that one package chip consists of 8 banks, but the output from one package chip is just 8 bits or 1 byte, because in one operation cycle, only one bank is active. With this understanding, let's go to the next part of our memory hierarchy, which is the concept of a rank. So now I am presenting to you an image which might be very, very familiar with you. Anybody who has assembled a computer or even opened a PC will see that the motherboard of your PC has slots in which you can insert these chips. These are the DRAM chips. Whenever you buy DRAM chips from Amazon or from any other vendor, these are the DRAM chips that you will get. This is a very familiar and popular sight. What are these PCB boards with 8 of these chips called? They are called dual inline memory modules, DIMMs, dual inline memory modules. Okay. So what is this dual inline memory module? This dual inline memory module consists of these 8 such package chips. So as you can see, 8 banks were consisting of one package chip and 8 such chips, 1, 2, 3, 4, 5, 6, 7, 8. 8 such package chips consist one side of a dual inline memory module. Why do I say one side? This is because the name dual inline memory module suggests that there are 2 sides or 2 faces to this dual inline memory module. The first face or the first front is called rank 0 and the back of the dual inline memory module is called rank 1. Okay, so now let's understand what is the number of bits that are form the output of each rank. As we had discussed just a few minutes earlier, 8 banks consisting of one package chip. Because only one bank is active at one period of time or one operation cycle, 8 bits are the output from each package chip. Since there are 8 such chips on one side of the rank, all these 8 bits coming out from the 8 package chips consist of the net 64 bits which will be finally sent to the processor. So let me recap what we just studied, remember, the output from one row or column or from one memory array was just 1 bit. A bank, which I'm showing in this image, consisted of 8 such memory arrays. Since 1 bit was coming out from each memory array, one bank would give you 8 bits of data or 1 byte of data. Now, a chip consists of 8 banks. However, only one bank is what is active at one operation cycle. So, the value of bits or the number of bits coming from one chip is only 8 bits. And since a rank consists of 8 such chips, the total number of bits which are given out of a single rank is 64 bits. Now, at a time, only one of these ranks are active. So either rank 0 or rank 1 is what is active during one time. Commonly, if you see in your modern day computers, there are only 2 ranks, rank 0 and rank 1. But in servers where the data requirement is very huge, there can even be more number of ranks. So the same dual inline memory module can have 16 chips instead of 8 chips. So on one side, there could be 2 ranks and on the other side, there could be 2 ranks. Therefore, the total number of ranks in advanced server chips could also be 4. Okay, but we will stick to only rank 0 and rank 1. Okay, which of the rank is to be selected is also being indicated by the memory controller to the DRAM subsystem. With this, we will move to the last part of the DRAM subsystem architecture, which is closest to the processor, and that is channel. So a natural question would be, your dual inline memory module itself is giving you 64 bits, which is what your processor will read. Any modern day processor generally reads 64 bits. So why do you want to add one more concept of channel? And the reason for that is the following. If you see what is the frequency of modern day CPUs, it is close to 3 gigahertz. In addition, you even have multi-core operation or multi-core, multiple number of cores trying to access data. 3 gigahertz and multi-core operation is a lot of throughput. However, after a lot of innovations till the hierarchy of DIMMs, the maximum DRAM speed that we can roughly reach is 800 megahertz to 1.6 gigahertz. Now there is a big gap between what is the throughput requirement from the CPU, which is at 3 gigahertz, versus what your DRAM chip can provide. The clocking of CPU is 3 gigahertz, whereas that of the DRAM chip is only 800 megahertz. And therefore, in addition to all these interesting concepts, you need more number of parallel channels which are established between the processor and the memory subsystem. This is very similar to the more number of, so moment you see that in an highway, the traffic is getting stuck. What do people do? They generally increase the number of lanes in the highway. So there are parallel channels for cars to pass through. In this case, you are creating parallel channels for data to pass through. Here too, you do innovation at 2 different aspects. One strategy is to use this very interesting concept of DDR. You might have heard of this concept of DDR. It stands for double data rate. So what is the concept of double data rate? Generally, whenever we have data communication in modern day systems, you have the rising or the falling edge of the clock, in which the data is being transferred one after the other. However, using this very special concept of double data rate, you are able to send out data in the rising and in the falling edge of the clock. So let's compare single data rate, where data is only being transacted in the falling edge of the clock, versus the dual data rate, where data is being transacted at the rising and falling edge of the clock. And naturally what happens is the bandwidth of the system becomes double without even changing your clock speed. Therefore, without improving the clock speed, which is roughly 800 megahertz, you can get a theoretical bandwidth of almost 51 Gbps. Why is this possible? Because your clock frequency gets multiplied by 2. And this concept of 2 comes because now you are sending and receiving data at the rising and falling edge of the clock. Okay, this is the first strategy at the topmost hierarchy, at the level of channel and DIMMs, to improve the bandwidth between the processor, or to reduce the bandwidth mismatch between the processor and the main memory subsystem. The second important concept is to simply increase the number of channels through which the CPU subsystem can independently transact and get data from the DRAM or the main memory subsystem. And this is generally implemented on the motherboard of your computing system. So basically, a channel is a dedicated slot where independently data can move in and out from the CPU to the main memory subsystem. Now, previous generations had only single channels, whereas current generations have dual or even more channels. As I just explained, each channel has independent read and write access to the memory subsystem, from the memory subsystem to the CPU subsystem. And therefore, if your modern day processor and motherboard supports multi-channel, it will naturally double the theoretical bandwidth. So this is a very interesting concept, because what was implemented a few generations earlier within the processor subsystem in form of multi-core parallelism is now being implemented between the processor subsystem and the main memory. Okay, so this was a lot that we have covered in today's class, but I hope you understand what is the value of having such a complex DRAM subsystem hierarchy, which helps you to reduce the big bandwidth mismatch between the CPU subsystem and your DRAM subsystem. Thank you. In the next class, we will do a quick recap of this DRAM subsystem architecture and start looking at the 1T, 1C cell. Thank you very much. See you in the next class.